Our topic is an interesting effect that occurs usually when you are in a motion relative to a wave source, or the wave source is in a motion relative to you. So this effect is called Doppler effect. You most probably have noticed that the pitch of an ambulance or a fire truck siren drops as it goes past you. Why? Well, that is a typical Doppler effect situation. And to analyze the Doppler effect for sound, we will work out a relationship between a frequency shift and the velocities of source and a listener relative to the medium. Well, to keep things simple, we consider a special case. Suppose our listener is moving with a certain speed towards the source and with the VL, and it's moving, the source is S and the source is stationary. The source is like it's some kind of speaker that releases sound, and the sound is spherical in the space. And it's moving uniformly with the speed of V, sound, speed of sound. Okay, so it's going in every direction. Okay, so these are all V's, speed of sound. So from crest to crest, we have the wavelength, lambda, okay? And then the speed of the source is 0. So I'm going to label it as Vs equals 0. Now, let's recall that we can represent the frequency of the source to be written as frequency of the source. I'm going to put the subscript S that we know it's a source, equals V over the lambda. So let's think first about a listener. So relative to the listener, the wave crest approaches to moving listener and has a speed. So we say the speed of crest relative to listener equals speed of crest plus speed of listener, which equals V plus V listener. So the frequency that the listener hears equals V plus V listener over the lambda. So let's simplify it a little bit, or represent the lambda in terms of frequency. So from here I can write lambda equals V over the frequency of the source, and then substitute that in here. We'll have a V plus VL over V over frequency of the source. That makes it V plus VL listener over V and times frequency of the source. So let's just make it a little bit nicer. So I can say the frequency that listener hears equals 1 plus the speed of the listener over the speed of the crest times the frequency of the source. So this is moving listener and stationary source. Now suppose that the source is also moving. Now we will denote the Vs to be the speed of the source. Consider that some time earlier, the source was actually somewhere here. And then some time has passed. The source moved a little bit further. So let's say right here. And then the source moved now here. Okay, so when the source was at the purple point, then the wave would have been this circle right here. And then when it moved, the circle would have been this one right here. And then for the green, we would have this circle. As you can see from this picture, the wavelength in the front are way different the wavelengths behind. So the wavelength in front is shorter than wavelength behind. So therefore, although the V is still the same, but wavelength is not anymore equal to V over frequency of the source. So to better understand this, let's take a look at one cycle of a wave emission, where the period of that cycle equals 1 over force of the source, frequency of the source. So during this period of time, the wave will travel a certain distance. Let's, for better understanding, let's draw a better picture right here. Let's say the source initially was at this point, and it would emit a wavelength at some frequency. This wavelength, let's call this one to be lambda. And the lambda will be the traveled wave, which equals V times the period. Okay, or simply V over frequency of the source. Now suppose that the wave, the source moves to point 2, like somewhere here, and the motion, I'm gonna write a Vs, and then so this new wave that the source emits, it would be observed a different wavelength. So this would be a different wavelength. Let's call it in front, okay? Lambda front. So to find the lambda front, let's write lambda front would equal the actual lambda minus the distance that our source has traveled, which is V source times the period. So then lambda front will be lambda minus V source times the period. So for the lambda, let's put V over frequency of the source minus V source, and then for the period, I'm going to put 1 over frequency of the source, and that would be simplified to V minus V source over the frequency of the source. Well, similarly, we can find the wavelength behind. So behind, and in this case, you should add the distance that the source travels. So lambda behind equals lambda plus v source times t. In this case, we will have v over frequency of the source plus v source over frequency of the source, and we have v plus v source over frequency of the source. Okay, to visualize this, let's imagine this is the original source, original wave, and from here to here we have the wavelength lambda, and then when the source moved from the original point to here, so this would be the distance it will travel, v source times t, and then this would be the lambda, and the new wave front wavelength will be from here to here, and that would be lambda behind. That's how I added lambda behind equals lambda plus v source t. Now to see what listener behind the source is listening, we're gonna refer to our expression for the f listener that equals v plus vl over v times frequency of the source. And so f listener equals v plus vl. Actually, I can write v plus vl over lambda behind. That's an easy way that we can write. And so I can say v plus v listener over, I rather use the frequency definition of the frequency. So, and then substitute the lambda behind it would be v plus v source over frequency of the source. That will give me v plus v listener over v plus v source times frequency of the source. Now to generalize this equation, let's just write FL equals V plus VL over V plus V source times the frequency of the source. Now this has many different situations. So in our case, we just discussed that we discussed two cases. First, the source was stationary and the listener was moving towards the source, and then we discussed the source is moving and a listener moving. Both are moving the same direction. So, but it could happen that the listener is moving away from the source, or the source can move towards the listener and the listener is moving towards. So there are a bunch of different situations that could be adjusted if we consider the sign of the listener's speed. So the listener's speed is positive if listener is moving toward the source, and negative if moving away from source. Now, same thing could happen with the velocity of the source. It's positive if the source is moving toward the listener, or observer, and it's moving when it's moving away from the listener, then we have a negative if it's moving away from listener or the observer. So pretty much you have to figure out what situation you have, and then make sure that you adjust be careful with your signs of the speed of the listener and the source, the velocities. Well, thanks for watching. Stay tuned for more to come, and there would be more examples, video examples presented later.